Good morning, students. In this video, we will learn about the electric force on a charged particle. As we know, if there is one positive plate and there is one negative plate, carries positive and negative nature. So the direction of the electric field is this, and the force works in the same direction of the electric field. For the positive charge, the force would be from positive to negative, and for the negative charge, the force would be from negative to the positive. Okay, so sometimes the force may be anti-parallel and the parallel, but always in a linear form. Okay, if the charged particle of mass m is here, which is in the rest, so the electric force works and it accelerates into the same direction. Okay, so its acceleration you can calculate by using one formula. Under this condition, the electric force always equal to the ma from Newton's second law, and the formula of electric force is called the QE is equal to the ma. So you can easily find the acceleration. It means the magnitude can change. Okay, if magnitude can change, so the energy can increases and sometimes can decrease. So need to know some points. The electric force always acts in the same direction as the electric field has. It can change the magnitude. Okay, and some points also. Suppose the electric field is here, which is from positive to negative, and if suppose you fired a alpha particle in this direction, so this is called its initial direction of speed, but it moved in this direction to get the proper direction along with the electric field. Okay, in this condition the path of the charged particle becomes the parabolic, but in this condition the path of the charged particle becomes the linear to the magnetic field. The electric force always works on the rest charge, right? Now, come to the next point. Motion of charge inside the magnetic field. So, I will write here the magnetic force on a charged particle. Magnetic force. As we know, the symbol of magnetic field, I can represent it by the crosses and the dots. So, we are expressing it with the cross. That means both the field is going inside, there is south pole, and inside the both the north pole. Okay, so we will do the two practice as the earlier scientists they did to find the nature of force and the direction. If suppose I fired the gun into the same direction as the magnetic field has, so it is found that there would be no magnetic force on that particle. If I fire the bullet of charged particle having some mass into the same direction, this is called its velocity. So here the velocity and the magnetic field are perpendicular. So you can apply the Fleming's left hand rule. The magnetic field is going here. This is called the velocity. So the magnetic force acts on the top. Okay, and the magnetic force is perpendicular to the magnetic field and the velocity. So I will draw here some crosses. So it has seems when this charge bullet enters into the magnetic field perpendicularly, so it begins to rotate in a circular form in this manner. And the direction of the force would be towards the center of its circle. Okay, so this is called the magnetic force. Right? Here we can notice some points. The first one, the force after the experiment I am telling. The force always perpendicular to the magnetic field and to the velocity. As well as the velocity and perpendicular, both velocity and the magnetic field both remains perpendicular. It means these all remains perpendicular. Point number 2, the force also depends on the charge magnitude. If there is no charge, no magnetic field, that means no magnetic force you can calculate. So the formula of the force by using these becomes the vector F is equal to Q dot vector B cross vector B, because V and B are perpendicular to each other. So this is called the vector form. And in the magnitude, you will write the F is equal to Q V B sine theta. If theta is the 90 degree, then your force would be maximum. If theta is 90 degree, so force F become QVB, and if suppose theta is equal to 0 or 180 degree, your force would be 0, right? Here the source of this force, this is the magnetic field, the source of the force is the QV. The source of the magnetic force is the QV. If there is no QV, so the force cannot be calculated. That means if the charge is in rest, as the velocity is here, if the velocity is 0, the force would be 0. It means the magnetic force will act only the moving charge particle. One more thing, here the velocity is not going to be changed. Only the direction can change, as you can see here. Okay, so the magnetic force can change the direction but cannot change the magnitude. Okay, if cannot change the magnitude, so the work done by the magnetic force over the charged particle always 0. Point number 2, if the work done is 0, so its kinetic energy always be constant, not going to be changed. Right? So these points are very important. So this is one of the points which we have completed. So you can note it down. I'm going to the next. The magnetic force on this is called the charged particle, and I'm taking the straight current carrying conductor. So my next point is magnetic force on current carrying conductor. Simultaneously, you can note it down. Okay, I'm erasing. As we know, a current carrying conductor, like this is a straight wire, okay, and it is carrying the current I, and we know the I is equal to Q by T, okay, and this Q is equal to I dot T, right? And if this current carrying conductor is inside the magnetic field, okay, I am drawing the magnetic field here. Right. So this is current carrying conductor, and the current is going up, and the magnetic field is going inside. So that means they are perpendicular. So again, to find the direction of the magnetic force, you can use the Fleming's right hand rule. The left hand rule. And what is the left hand rule? If you stretch your this forefinger, middle finger, and the thumb perpendicular to each other, so this is the magnetic force. This is called the motion of the charged particle, either direction of the motion of the current, either direction of the velocity, and this thumb shows the direction of magnetic force. Okay. So now tell me where the magnetic force is acting. This is called the field. This is called the current. So the force will act in this side. So this is the direction of the magnetic force. If you keep these 2 points here, and the center point is fixed, so it can rotate also. Now, as we know, the formula of the magnetic force working on a charged particle, QVB sine theta, but there is QV as sine theta I have ignored. In the vector form it is written. So the Q is not only the Q here, because the current is Q by T, so you can write the Q as IT. The vector F is equal to I dot T vector V cross vector B. Okay, then vector F is equal to I dot, this is called the T vector V, where the V is the velocity of the charged particle. As we know, the velocity of the charged particle can be written as in the Vd form, drift velocity. So I will write here the Vd into the cross B. Okay, and the speed is equal to distance upon time. So that speed into time is equal to the distance, where the distance is equal to the length of the straight current carrying conductor. So I can write the L here. And in the direction from bottom to top, so it has the direction called the vector L. So here I can write vector F is equal to IVD T dot vector VD. I can write as the vector L. So this is I cross vector L cross, not the cross, called the dot vector B. So this is the formula which is acting on our straight current carrying conductor IL cross B. Okay, so this is now do one thing here. You can compare these two formula, formula number 1 and this is formula number 2. This is called the magnetic force as here, this is called the magnetic field as here. So what is the QV and what is the IL? So here the Q vector V always equal to the I vector L. So I can write the IL as the QV in the magnitude form because they have the same direction. So I ignore the direction. Here the QV is equal to IL. Right? So keep remember these all points. If you fix the center of this current carrying conductor so it can rotate, so the torque will go in one of the end inside and one of the end is outside. Okay. Now next, so I am erasing it. You can note it down. One thing I forgot to mention in between, and that is the heliaxial motion of charge particle. And I am mentioning it heliaxial motion. Heliaxial motion of charge particle. Motion of charge inside the magnetic field. Let's suppose this is called the origin, x-axis, this is called the y, and this is called the z. Right? And in this direction the magnetic field is here, so I will draw only the single line at the top and at the only at the top. Okay, so the magnetic field is going inside. I can fire the bullet up to here, I can fire the bullet up to here. So this is called the perpendicular and this is called the parallel. If I make any angle and I fire the bullet, charge bullet here with velocity v making some angle theta, so what would be? There is the v is not perpendicular over the b exactly. So you can resolve this velocity along with v cos theta in the x and the v sin theta in y. Okay, so what type of motion? Now the charge particle is moving at the top by the v sin theta and the charge particle will shift in the x-axis because of the v cos theta. So its circular motion will not be exactly circular, it comes in the heliaxial form like this manner. So I can draw it like a dot, so it comes like this. So its motion comes like this here, so you can see. This is called the heliaxial motion of it. Okay, now it is moving in this direction because of v cos theta, it is going up, going like this up because of the v sin theta. Okay, so this is called the heliaxial motion. And how this is called the gap between the two rings is called the pitch. The gap between the two rings is called the pitch. And how to find the pitch? The pitch is equal to time into the speed, which is the speed is v cos theta. And this is called the radius of the circular path. You can find by applying the formula how to find the radius. Okay. And the radius you can find by the magnetic force called the QVB, and at the center it works the centripetal force, so it's called the mv square by r, and you can easily find the radius and the speed also. So I'm erasing here. Some other factors to understand the magnetic force is the magnetic force acts towards the center and it is always equal to the centripetal force mv square by r. Right? So your velocity is equal to qrv by m. So I am right? Yes, qrv by m. And its kinetic energy is equal to half m dot v square, so you can do the square of it. Q square, r square, v square by m square, so 1 m will cancel. So this is called the velocity, the kinetic energy. The direction changes, but the kinetic energy and velocity always remain same. You can also find the time period to complete the one circle, one revolution. As we know, the v is equal to r omega, So the omega is equal to V by R, and the omega is equal to 2 pi nu, right? Either you can write the 2 pi by T, so the V by R, and you can say that T is equal to 2 pi R by V, and you can put the value of the V from this equation, so the R will cancel. Okay, so you can find the T also. How to find the time period and the speed and the kinetic energy. Now, coming the next point, which is the next is the magnetic force on a two current carrying conductor. So this is our next point. Magnetic force on two current carrying conductor is, let's suppose there is one the straight current carrying conductor, and there is another straight current carrying conductor, and they can carry the current in the same direction as well as in opposite. So I am taking the same direction of the current. Let's suppose they have the current I1, current I2, and they have the same length called L. So I can take L1 and L2. If it is going up, so by applying the right hand thumb rule, you can find the direction of magnetic field, and the magnetic field is going like this around the wire, like a dotted line has, and it has the same direction of the current going up, so the direction of the magnetic field is like this. So we can write the I2 here, I1 here. You can draw the more rings. Now tell me, where would be the direction? The field has this direction, so going inside from this point. So I can draw here, I can draw here, 4 arrows. You can show on the diagram. Okay. So I can draw the other ring. Exactly the same direction, all rings will follow. So see, at this point, it is going here, and at this point it is coming here. So at these regions they are following in the same direction. If I draw the next ring, so I can draw like this. So you all can see the direction of magnetic field produced by these two currents can come in the same directions. So due to this same directions, these two current carrying conductors will attract to each other. So note one point. If the two straight current carrying conductor, they are carrying the same current in the same direction, the current may or may not be same, but if the direction is same, so they will attract. And if suppose any one direction is opposite, so they repulse. So here they are attracting, and in this diagram, in the next diagram I am going to draw, they are repulsing. Here. Is this going up? It is going down. So it will create the direction like this. Current is going here, and its current is going here. So you can see. Oh, sorry. It is going down, so it is coming here. At this point. So these are going inside here. Okay. So this is the pole. This is another direction, and they are repulsing. So in the next circle, yes, आएगा. In the next circle, ये ऐसा आएगा, and try to maintain the gap separation, and there would be one line which makes separate. So here they are repulsing to each other, and here they are attracting to each other. So notice one point: if the direction is same, so two current carrying conductors will attract. If the directions are opposite, the two current carrying conductors will repel. The force exerted by these two wires always be same, and the same cases you can add in this diagram. How to find the magnetic force current working on acting on a current carrying conductor? As we know, let's suppose this is called the straight current carrying conductor, is called the first wire, is called the second. You can write the A and the B. The force exerted by the A over the B is equal to mu naught by 4 pi dot I by R. So the gap between these two wires is called the R. Okay. And the formula is sine phi 1 plus sine phi 2. If these two wires are infinite, and suppose the points P which we are finding at the bisector. So the phi 1 and phi 2 would be 90 degree. So sin 90 degree and sin 90 degree becomes the 1 and 1, then becomes 2. So we write here the B is equal to mu 0 2I by 4 pi r. So you can apply the magnetic force formula, which is F is equal to I vector L cross vector B. So the sin theta, again you will take the 90 degree down, Z becomes the 1. Then ILB, where L is the length of the wire. See one point. Suppose at the point A, the wire A is exerting the force on the B. So the force on the B becomes the F2 to attract it. Okay, so I am going to find the F2. This is the magnetic field due to the B1, due to this wire. So this is called the B1, magnetic field of A, magnetic field of A is called the B1, and magnetic force on B is called F2, ILB1, and the F2 has current called I2, and let's suppose they have the same length, either you can write the L2. So the F2 is equal to I2 L, B1 की वैल्यू ये है mu 0 by 4 pi dot 2I by R. Okay, so you can arrange the F2, you can write mu 0 by 4 pi dot 2I by R. अब यहाँ पे B1 के लिए है, तो B1 का करंट हमने बोल दिया है I1 है, तो आप यहाँ पे I1 लिख दो, मैं भी यहाँ पे I1 लिख देता हूँ, और ये I2, then I1 dot I2 dot L. This is the formula which is acting on a straight current carrying conductor. अगर ये फॉर्मूला एक निकल आता है तो आपको हर वायर के लिए फॉर्मूला नहीं निकालना है, क्योंकि जितना फोर्स एक वायर इस पे लगाएंगे उतना ही दूसरे पे लगाएंगे, चाहे वो अट्रैक्ट करे या फिर वो रिपल्स करे. तो यहाँ पे ये रिपल कर रही है तो इनका डायरेक्शन अपोजिट होगा, और यहाँ पे अट्रैक्ट कर रही है तो इनका डायरेक्शन इस साइड होगा, अंदर की तरफ होगा. सो दिस इज द फोर्स. You all can convert this formula into the other form, right? So I'm going to erase it. See here, as we know about the electrostatic force, the force working between the two charged particles always written in the form F is equal to 1 upon 4 pi epsilon 0 Q1 Q2 by R square. Here the force is also, the magnetic force also depends, yeah, we can say inversely proportional to the 1 upon R square. तो हम यहाँ पे इसको ऐसे लिख सकते हैं कि the electrostatic force is 1 upon 4 pi epsilon naught dot Q1 Q2 by R square, where the 1 Q1 is the source of the force and the Q2 is also the source of force, and the resultant force depends on the Q1 and Q2. In the magnetic force, the source of the magnetic force is called the I2L. Got my point? ठीक है, तो अगर मैं यहाँ पे Q1 की जगह IL लूं, I2L लूं, या Q2 की जगह I1L लूं, तो दोनों यहाँ पे हमारे देखिए कैसे हो जाता है. Now the magnetic force becomes the mu 0 by 4 pi if I apply the inverse square law. So it becomes the I1L1 if the lengths are different than I2L2 divided by R square. और अभी भी थोड़ी देर पहले हमने क्या किया था कि IL बराबर क्या था QV. So you convert this formula F is equal to mu 0 by 4 pi Q1 V1 Q2 V2 divided by R square. So these two formulas are also used to find the magnetic force between the two charges. The magnetic force between the two moving charge particles, either the current carrying conductor. Okay, so these are points completed. The next and the last point is the comparison between the magnetic force and the electric force. So I am going to erase it. Comparison between magnetic force and the electric force. So I am writing here the magnetic force, electric force first. Electric force. Here I will write the magnetic force. Some points which is very easy to you people. The point number 1, the formula F is equal to QE. Its formula is F is equal to QVB. I am writing in the magnitude form. Sin theta, either you can write ILB sine theta. If suppose theta is 90 degree, then it comes QBV and IND. Okay. The source of the electric force is the charge, and the source of magnetic force is the QV and the IL. So point number 2, the source is the Q and the source of magnetic force is the QV and the IL. Right? Point number 2, so this third, whether the charge moves parallel to the field, anti-parallel to the field, and if it comes perpendicular to the field, the electric force always acts. क्या बोला मैंने? अगर चार्ज पैरेलल हो या एंटी पैरेलल हो या परपेंडिकुलर आए या जाए तो इलेक्ट्रिक फोर्स तो भी लगता है, बट यहां पर मैग्नेटिक फोर्स कब लगता है कब नहीं लगता है? पैरेलल में नहीं लगता. इफ वेक्टर v इज पैरेलल टू वेक्टर b, और ठीक है, if the vector L is parallel to vector b, the force cannot be act. So this is for the point number 1. Point number 2, this is point number 3. The force always would be 0. If the vector v is parallel to vector e, the force always exists. Here I cannot write the b, I am writing the direction of the motion. Okay, so the force always be 0. If it perpendicular, even though the electric force acts, but if it perpendicular, only the magnetic force will act. Point number next, it acts on the rest charge and it acts only on the moving charge particle, So these are the major points which is need to understand, right? Okay. So many more points you can write. I'm going to describe you again new. The major and special case is if charge is at rest, REST, the electric force can work and the magnetic force would be 0. That means on the rest only the electric force works and at the rest the magnetic force would be 0. Point number 2, if this charge particle comes inside the electric field, so only the electric force works and magnetic force would be 0. If this charge particle comes in the magnetic field, so only the magnetic force will work and electric force would be 0. Suppose the electric field and magnetic field both are parallel to each other, and if I fire the gun, ठीक है, अल्फा पार्टिकल जा रहा है, देखिए यहाँ पे दो फील्ड है, पहले मैग्नेटिक फील्ड है और यहाँ पे इलेक्ट्रिक फील्ड है, और अगर इसको मैंने फायर कर दिया तो क्या होगा? जैसे ही एक फील्ड में एंटर करेगा बी में, मैग्नेटिक फील्ड में, तो परपेंडिकुलर हो जाएगा, तो मैग्नेटिक फोर्स विल वर्क, सो इट बिगिंस टू रोटेट, तो इसकी पॉसिबिलिटी तो है नहीं कि वो इलेक्ट्रिक फील्ड में जाएगा. अब जब ये बंद होगा तो यहां पहुंचेगा तो इलेक्ट्रिक फील्ड में पहुंचेगा तो इलेक्ट्रिक फोर्स काम करेगा, ठीक है. और अगर दोनों फील्ड को, वेक्टर ई और वेक्टर बी, दोनों को हमने परपेंडिकुलर कर दिया तो क्या होगा? उस वक्त आपको ये देखना है कि जो वेलोसिटी है उसका डायरेक्शन क्या है. अगर वेलोसिटी जो है इलेक्ट्रिक फील्ड के पैरेलल है तो उस पे इलेक्ट्रिक फोर्स एज वेल एज द मैग्नेटिक फोर्स कम एज वी डिड इन द वेलोसिटी सिलेक्टर, ठीक है. ध्यान रखना, इसका मतलब ये है कि किसी भी मूविंग चार्ज पार्टिकल में दोनों तरह के फोर्स लग सकते हैं व्हेन द इलेक्ट्रिक फील्ड एंड द मैग्नेटिक फील्ड परपेंडिकुलर टू ईच अदर, right? So that force is the Lorentz force. Now the next point is the Lorentz force. Come to the next, Lorentz force. Lorentz force. Lorentz force, it acts when the charged particle moves in electric and the magnetic field. So the resultant force is the electric force plus the magnetic force. So the vector F is equal to Q vector E plus Q vector B cross vector B, ठीक है. अगर E और B दोनों परपेंडिकुलर हैं तो रिजल्टेंट फोर्स आप इस तरीके से निकाल सकते हैं, ठीक है. चलिए, और यहाँ पे एक सबसे इंपॉर्टेंट देखने वाली बात है कि अगर दोनों फोर्स परपेंडिकुलर है और हमने इस तरह से एडजस्ट किया कि वो दोनों एक दूसरे को इक्वल करेंगे, कैंसिल करेंगे, तो दिस QE becomes equal to QVB if vector E is perpendicular to vector B. right? So possibility ये भी है that you can find the velocity, right? And the next point, which is very we can say crucial point, कि ध्यान देने वाली बात ये कि इलेक्ट्रिक फोर्स और मैग्नेटिक फोर्स दे आर इंटरकन्वर्टिबल एंड दे आर रिलेटेड टू ईच अदर। क्या होगा कि अगर कोई चार्ज पार्टिकल रेस्ट में हो और अगर मैं ऑब्जर्वर हूं और मैं देख रहा हूं तो रेस्ट में सिर्फ इलेक्ट्रिक फोर्स काम करेगा, लेकिन अगर मैं रेस्ट में हूं और पार्टिकल मैग्नेटिक फील्ड में मूव करता है तो घूमता है, मतलब उसकी डायरेक्शन चेंज होती है, तो वी विल से इट इज द मैग्नेटिक फोर्स। लेकिन चार्ज पार्टिकल जितनी स्पीड से दौड़ रहा है और उतनी स्पीड से अगर मैं दौड़ूं तो मुझे मैग्नेटिक फोर्स नजर नहीं आएगा, मुझे सिर्फ इलेक्ट्रिक फोर्स नजर आएगा। तो इसका मतलब है कि डिपेंड्स ऑन द रिलेटिव मोशन ऑफ द चार्ज पार्टिकल between with the observer and the charge. Okay, so till here we completed. Thank you. Note it down please.